So next we are going to discuss unitary time evolution. This is one of the most central concepts in quantum mechanics, so it's extremely important. And the idea is that if we know the wave function of a system at some point in time, then we can predict the wave function at any future time if we know the solution to the time-independent Schrödinger equation. And not only that, we can even predict what the wave function was any time in the past. So what do we mean by that? So suppose we have a wave function, say psi x at time say 0, and let's call that say psi of 0. And let's call that psi of x. Now, if we have solved the Schrödinger equation, we have all the energy eigenfunctions, and we have seen in a previous lecture then we can express psi of x as a linear combination of all the energy eigenfunctions, which we are denoting by phi I. So what are the phi i's? They satisfy the time independent Schrödinger equation with with the energy eigenvalues given by EI. So if you do this, then with this expansion, we can say that the psi of x at any time t, say in the future, will be given by the summation of the energy eigenvalue, the linear combination, but with each term now multiplied by the time evolution factor, which is given by e to the power minus I ei t over h bar. So this is the formal solution to the Schrödinger equation. So we are going to now rewrite this solution in a different form, and we are going to show that there's an operator which evolves every wave function to its future or past time evolution if evolutionary wave functions. So how do we do that? So let's just look at this guy. So without the sum, let's just look at this factor. So this is some number some phase e to the power minus I ei t over h bar times phi I of x. Now we can write this as the first factor is a series. So it's a power series, an infinite power series, where these are each of the terms. So all that we have done here is we have just expanded this exponential into a power series. But then let's observe that phi I is an eigenfunction of the Hamiltonian operator, meaning that h acting on phi I gives me ei times phi I of x. Now, because an operator always commutes with itself, this means that if I apply h twice on phi I, then I get the square of the eigenvalue times phi I. In general, if I apply h n times, where n is an integer, on phi I, then I get the eigenvalue raised to the power n times phi I of x. So this means that we can rewrite this expression in a slightly different form. We can rewrite this as, we can replace each of these factors, e to the power n phi I, by the Hamiltonian raised to the power n times phi I. So we can write e to the power minus I ei t over h bar as summation, where n goes from 0 to infinity, and then here we have minus I t by h bar to the power n divided by factorial n. And now here we have the Hamiltonian operator raised to the power n, and now this was acting on phi I, so we need that. So the Hamiltonian is acting on phi I of x. So here we are using this relationship. So now we can write this as e to the power minus I h t by h bar acting on phi I of x. So this is now an operator, and it's an operator defined in the following way. So the operator e to the power minus I h t over h is a formal power series of infinite number of terms of h raised to the power n, where the coefficient of each term is given by minus I t over h bar to the power n divided by factorial of n. So thus we can see that any state can be given, if you're given any state, the future of the state is given by the time evolution operator, this operator that we are writing as e to the power minus I h t over h bar, acting on the state when it was at time equals to 0. So this is known as the time evolution operator, and it's written as, usually written by u t comma 0. More generally, u t comma t0 is given by e to the power minus I h times t minus t0 divided by h. In this case, we are taking t0 to be 0. So this is the time evolution operator, and it's a very important operator. As its title suggests, it evolves state at a given time to a future state. And this is the formal solution to the Schrodinger equation. So the time evolution operator gives me this thing. The psi at time t is given by u t comma t0 acting on psi x comma t0. Now let's discuss some properties of the time evolution operator. Now, using the fact that if you have two operators a times b, and we take its Hermitian conjugate, then we get b dagger, a dagger. And the fact that h dagger is equal to h, one can show that if I take the Hermitian conjugate of the time evolution operator, so if I take u, let's just take t, comma 0, and take its Hermitian conjugate, then of course I can write out the power series, and but you can verify that if I take EHT by h bar and take its Hermitian conjugate, then what I get is e to the power plus I h dagger t by h bar, but h dagger is h because it's a Hermitian operator, so I get I h t by h bar. And so this is u dagger, and then you can show using the BCH or Baker-Campbell-Hausdorff formula, which will be given in an appendix to this lecture, that u dagger t, we just write ut to be, say, u of t comma 0. Then u dagger of t times u of t will be given by 1, or identity. And you can also show that u dagger is then 1. So this implies that the u dagger operator is the inverse of the u operator. So operators which satisfy this relationship are called unitary operators, and the time evolution operator is a unitary operator. So the So what's the interpretation of unitary operators? What the unitary operators do is that they preserve information that is contained in some state. They preserve information that is contained in some physical amplitude. They contain information that is contained in some norm. So they are the manifestation of the evolution that is embedded in Schrodinger's equation. So, for example, if I take two states, psi and phi, and I consider their inner product, so all physical quantities in quantum mechanics are contained from inner product of different states. So, we can show that this inner product under time evolution remains invariant. So we can write this as U acting on psi at time 0, U acting on phi at time 0. Now, because it's an inner product, using the rules of inner product, I can take this guy over here, but the price I have to pay is that there's a dagger sign over here. And then there's ut phi of 0. But now since u is unitary, we can use the fact that the unitary operator is its own inverse, and then write this as psi of 0, u inverse of t, u of t acting on phi of 0. But this is nothing but 1, and therefore we can write this as psi of 0, phi of 0. Therefore we see that the inner product at time 0, its value is equal to the inner product at a later time. So one of the comments that I wanted to make is that in general, if you have a Hermitian operator, let's call it H, it doesn't have to be Hamiltonian, it is some arbitrary Hermitian operator, then you can always create a unitary operator by exponentiating it and multiplying, first multiplying it with an I and then exponentiating it. So this is going to give you a unitary operator. So if this is Hermitian, so this is Hermitian, then this is unitary. And also, if you have a unitary operator u, you can always take the log, and and that is going to give you a Hermitian operator up to a factor of I. The other comment I wanted to make, so this is say comment number 1. The other comment I wanted to make is that U dagger, which is the inverse of the unitary operator, the time evolution operator, it evolves states, backward in time. So what does this mean? So if you have a state at, say, 0 time, and you apply U dagger t, then you're going to end up getting the state at time t minus at minus t. So this is also related to the fact that information is not being lost, because you can, using a unitary operator, you can evolve your system forward and backward in time.